So welcome everyone. I'm going to spend today's seminar to talk a little bit about my master's thesis supervised by Dan that I've just submitted to the School of Computing and Information Systems at the University of Melbourne. It's a big thesis in the end. I've just put a draft copy in the Discord channel, which is still a draft because I've still got to go through and do a proper proofread. And at the moment I've been working on cleaning up the bibliographic information. So that's why I still consider it a draft. But anyway, I thought today I would kind of give a high-level overview of the technical content of the thesis, and I'll hopefully do that in not too much time, and then we'll have time to talk about some specific results that are interesting, and we can do a deeper dive into certain results in future sessions. So the title of the thesis is Structural Degeneracy in Neural Networks, and let me unpack that a little bit. So by neural networks, I'm talking about artificial neural networks. The setting for this thesis is, this is like a theoretical analysis of the relationship between neural network structure, as in parameters of neural networks, and neural network functions, as in the input-output maps that a neural network implements. So it's well known that there are multiple parameters that implement the same function for many neural network architectures. Because, for example, you can usually just swap the weights of certain neurons in the same hidden layer, for example. And because the addition that is implementing the computation is commutative, this has no effect. It's as if you've exchanged the neurons or just changed the order in which you've implemented the neurons or something like that, and it has no effect. And so a mathematically interesting question in its own right is, well, okay, that's one way to describe two neural networks that have two parameters that have the same function. Maybe what are all of the different ways that you can implement a given function? Or another question might be, what's the most efficient way in terms of the number of hidden units? What's the smallest number of hidden units needed to implement a particular function with some architecture? These are the kind of questions that I try to address in my thesis, because I found that in the literature in the past, they've been addressed in a kind of, I don't know if superficial is a fair characterization. Anyway, the answers in the past have had certain assumptions, and they haven't been complete answers, I think, in particular on this minimization version of the question, because people have basically assumed in the past that they're only concerned with minimal networks. So right off the bat, they're going to assume away any structural redundancy, or what I call structural degeneracy, in the networks. So my thesis has basically been about relaxing that assumption. We're saying, what if we have an arbitrary parameter, not a minimal parameter a priori? And then we can ask, like, well, what is the minimal implementation of the same function? Can we kind of minimize the parameter or something like that? And we can ask, what are all of the functionally equivalent parameters, all the parameters implementing the same function? So that sort of breaks down the title of my thesis, Structural Degeneracy in Neural Networks. Any questions so far? I'm going to sketch the contents of the technical chapters on the board. So I can say that the setting for my thesis is a particular family of neural networks. I started small. I started with single hidden layer hyperbolic tangent networks. But I could have started smaller. I could have started with networks with no biases on their hidden units or output units. And I could have started with networks with a single input unit or a single output unit. But actually, I've studied it's not too much more complicated to study neural networks that have multiple output units, multiple input units, and biases. So that's my setting. So within that setting, my thesis has 3 main technical chapters, which are chapters 4, 5, and 6 in the document. Chapter 4 is called Neural Network Reduction and Rank. So in the setting of these simple single hidden layer tanh networks, reduction corresponds to the process of taking a parameter and eliminating all of the structural redundancy and finding a minimal parameterization. So I've given algorithms for this in my thesis. And rank is the size of that minimal network implementation of a given function. So you can think of rank as the number of hidden units needed to implement a function in this architecture. That's the rank of the function, or the rank of a parameter. So if you start with one parameter, maybe it's full rank, meaning that you need just this many units to implement the same function. Or maybe it's using 10 units, but you could do the same thing. You could implement the same function with 5 units. That means this parameter has rank 5. Okay, so this is the first chapter. And it's these are kind of idealized concepts where we're working with precise equality, the kind that gets a little troubling if you go to implement things and you're using floating point numbers and on computers. But these theoretical algorithms are still conceptually useful and interesting, as I explore in some of the later chapters. Okay, that's chapter 4. Chapter 5 is called Degenerate Neural Network Geometry. This is meant to be, I think this title is a little bit vague compared to my other ones, but allow me to unpack geometry a little bit. I consider it a geometric question to take the parameter space and kind of carve it up into functional equivalence classes, where you have, so you say you have a parameter space. Each point in here is a vector corresponding to the weights of a neural network. Maybe there are these sets. Maybe they look like this. Maybe they look like, maybe it's just a point. Actually, I'll use a different color here. Maybe another set is just a single point or a small group of points. And all of the parameters in these sets correspond to, well, they implement the same function. Then these are called functional equivalence classes. And in the past, people have studied the non-degenerate case, and they've completely characterized these sets for non-degenerate networks, which look like the red case. They're discrete. They have a combinatorial number of elements, but it's a finite number. And they're described by these unit swapping operations that I talked about before, and a couple of other simple operations. With tanh, because it's an odd function, you can do some negations as well. These are well-known symmetries of the implementation. But in the degenerate case, it's much more like the green case. I mean, this is a very abstract diagram, and I don't know if you're going to have these curves, but the functional equivalence classes are extended. They're not discrete. They have an infinite number of points, a continuum of points, parameters that implement the same function. And I've tried to describe them in this chapter. I also give an algorithm for, this is, in one sense, this is a different perspective on the same thing, but in another sense, it's sort of something different. I've given an algorithm that takes a given parameter, maybe by this green dot, and actually, it might, if you run the algorithm again on a different parameter that's in the same functional equivalence class, this algorithm will map those both to a consistent representative from inside the equivalence class. Maybe that's this good dot here. But importantly, this algorithm transforms all of the parameters in the green set to the same representative, and all of the parameters in any other set would be transformed to a consistent representative in that set. I call this a canonicalization algorithm because it's finding a canonical representative or representation of any parameter in terms of the function it implements. And it could be used, for example, to check in an idealized setting whether two parameters implement the same function. You could just use this algorithm, compute their canonical representatives, and then check them for naive equality, like do they have the same components as a vector? It's closely related with describing the full set, because the full set is just those parameters that are going to map to the representative. The full green set I'm talking about. Okay, one last chapter, and I think this is the one that Dan finds the most exciting. What did I call this one? Chapter 6, degenerate neighborhoods in parameter space. So you just write that. So I already mentioned that these are kind of idealized algorithms. Even the geometry here is idealized. These are exact equivalents. There might be other sets of parameters that are implementing so almost exactly the same function, just maybe different by a few, like a fractional amount on some inputs, very close on other inputs. Maybe also we care about certain inputs over others, and on those inputs, it's basically the same function. This is all not considered part of this question because I'm working in the sort of exact case. But it's actually interesting in practice. But sort of one thing that's interesting in practice is we may not have such exacting standards. We may consider two neural networks to be kind of practically identical if they're almost identical, sort of mathematically speaking. If they have similar output on almost all inputs, that's also interesting. We'd like to know what parameters have that property. And another point is that degenerate neural networks are kind of atypical. These non-minimal networks actually occupy all of the, let me put it this way, all of the green sets. So the blue space, the blue parameter space is made up of red sets and green sets. Red sets are the ones that are discrete, and they occupy, well, they're discrete and they correspond to minimal implementations of neural network functions. The green sets are continuous and they correspond to non-minimal implementations of neural network functions. It may look like the green sets are bigger than the red sets, but the thing is, all of the green sets together is a measure zero subset of the parameter space. So even though each individual green set is sort of infinitely bigger than any individual red set, the red sets kind of dominate. They're everywhere. Well, they're almost everywhere, sort of mathematically speaking. But the neighborhood of the green sets is not measure zero. If you consider not the parameters that are non-minimal, because they're very rare, but the parameters that are kind of nearly non-minimal, they're nearby some degenerate neural network. That's also an interesting set. And so I turn to that set in my chapter 6. I say, for example, how could you define like how close a neural network is to being degenerate? Could you describe that set? And I show that, for example, if you want an algorithm to decide if a given neural network parameter is within a given radius of one of these sets, well, actually, I've got to be careful because that's not so hard. That's easy to check. But you can sort of ask how non-minimal are these functions? We were talking about the rank before. So if you want to ask, my parameter, maybe it's nearby a non-minimal, nearby a degenerate network. Maybe there's degenerate networks and there's like very degenerate networks that have very low rank. Determining how close a parameter is to an arbitrary low rank sort of part of the parameter space is going to be NP complete. That's what I prove in my thesis. So if anyone here is not familiar with computational complexity theory, that means that this problem is sort of, it would be considered computationally intractable. We don't really have any idea how you can efficiently solve this problem of determining how close you are or whether you're close to a low rank section of the parameter space. And this is sort of, that means that this problem is somehow related to, you know, classically intractable problems like Boolean satisfiability, traveling salesman problem. Those are just to name a few kind of more well-known ones. Anyway, that's the topic of chapter 6, which is basically just defining this measure of nearby to degenerate networks and then proving that computing it is intractable using some computational complexity theory. So yeah, there's an overview of what I accomplished with my thesis. I wonder if there are any questions already. If not, we can get into some of the topics in more detail. Okay, I guess let's get into some of the topics in more detail. So I thought that there's a bit of, I've been talking at a bit of a high level here, and I might have even lost some of you with the different terms that I'm using. So I do want to spend some time kind of laying some preliminaries, hopefully not too much time. I think I would have time to go through the following. This is kind of my goal for today. And if we have more time, I'm also open to input to kind of steer this in a different direction, but here's what I propose. I want to talk to you about, I want to kind of formalize degeneracy. And I want to show you the kind of state of the art before my thesis theorem for 10H, for these hyperbolic tangent networks. And this theorem is really the foundation for all of my work in my thesis, which is basically been about kind of applying this theorem and turning it into algorithms and seeing where it leads. So, and that theorem is the result from Sussmann in 1992, which shows that there are 3 equivalent characterizations of neural networks that correspond to this degeneracy. And I've already kind of hinted at this. One of them is non-minimal networks. So networks that could be implemented with fewer hidden units in some way. Another one is networks that have a kind of richer functional equivalence class, like the green sets versus the red sets in the diagram. And the third characterization is these networks have these sort of simple patterns in their parameters that means they're really easy to detect. You just check the parameters and you say, do any of them meet these conditions of reducibility, or what I'm going to call them? And if so, then you know that they're degenerate. So these 3 characterizations are all equivalent. They all describe the exact same set of neural network parameters. And that's the basis for kind of the technical results in my thesis. So I want to go over that now. This leads to the definition of rank and, well, reduction, the reduction algorithm, which is kind of minimizing neural networks. And I think that would be a sensible aim for today, is to go through that. with plenty of time for questions and discussion as well. So hopefully, yeah, that's my goal. Any input on that from anyone? All right, then let's do some definitions. Okay. I guess I'll start with the setting. So this is the family of neural networks that I consider, and I'll make some comments on how you could extend this to other settings. So a neural network parameter. Actually, I'll start with a neural network architecture, which is basically going to focus on just a number of hidden units. Basically, it's just a number h. It's a natural number. If you define the boundary cases carefully, you can allow it to be 0. That's not really super important for today, I don't think. But yeah, anyway, it's just a natural number, and it's the number of hidden units. In a 10H network, a single hidden layer 10H network. We're going to assume that there's in the background some number of inputs and output units as well, but that's always going to be fixed. So I'm just going to put a note here, and then we'll just keep this implicit. So also n, this one should be non-zero, and m, which are numbers of inputs and outputs. And so you'll see these come up in our in the notation sometimes, but I guess I'll try and de-emphasize it. But anyway, then you end up with a network that looks like this. You have your input units. There are n of those. They're fully connected to your h hidden units. And these are fully connected to your m output units. And so this is the network structure that we're talking about. These units are going to be biased 10H units. So they're going to be biased units with a 10H activation function. And these ones are biased linear units. Well, specifically identity, like I don't apply any activation function on their output. So this gives us an architecture, and h is the variable that I use throughout my thesis to represent this. A parameter is then a vector in, let me see, how many parameters are there going to be? How many individual numbers are there going to be in a single parameter vector? I'm deciding what dimension to give this parameter space. There's going to be n times h weights in that first layer, plus h times m weights in that second layer of connections, plus h biases in the hidden layer, plus m biases in the output layer. So this is the total, and I'm just going to call that space WH. If you want, you would also put an n and an m in there, because it depends on those as well. So this is a parameter. It's just going to be the right number of parameters for this to specify all of the different parts of the network. And finally, a neural network function which I'm going to write as fw with w as a parameter. This is a function from Rn, the input space, to Rm, the output space. And I guess I'm going to need the next board to describe the function. But I'll try and also speed up a little because this is basic stuff. Oh, I haven't been checking the chat. I'm just going to check that. Try and keep that open. Actually, while I'm on the boards, I can't see that. So yeah, please feel free to call out, interrupt me at any time via the voice. Periodically check the chat if no one else reads out chat messages. Okay, so we have a parameter. I guess I use this convention throughout my entire thesis, and I'm going to rely on it again today. I want to write a parameter vector sort of specifically by its components. And I'm going to call them A1 through to AH, B1 through to BH. I better make sure that's a H and not mistaken for an N. C1 through to CH and D. And these components have certain meanings. Maybe the quickest way to say what they are is to say that the function implemented is this. It's the sum from I equals 1 to H. So for each unit, we're going to have an outgoing weight multiplied by the activated value of the incoming weight vector times the input x plus the bias. And then this whole thing, you've got to add an outgoing weight vector, outgoing bias vector to it. So let me annotate this a little bit, and we'll also make sure it all adds up. This AI is a vector in Rm. If you look back on the original, it actually corresponds to these two on the previous board. These two values are in the vector AI. So it would be AI1, AI2, or something. And this is not a vector product here. Tan-H produces a scalar. So this is the scalar value of the hidden unit multiplied by this vector, and that becomes the vector output of vector value contribution from this unit to each of the output units. I don't know if that's like a little bit non-standard to do it that way, rather than some kind of defining this from the perspective of each output unit. I've instead defined it from the perspective of each hidden unit. Anyway, on the inside, we have things a little bit more standard. This is just an inner product here. And I'll point out that this BI is the incoming weight vector for the hidden unit I. So that means it's in Rn, because there's one value coming from each input unit, and there are n of those. And that checks out because x is an input vector, which has to be in Rn. Ci is a constant. That's easy. We've done a dot product, and then we're adding constant. So the input to 10 is then going to be a constant. And finally, I need one more color. Here we go. D is a vector, one value for each output unit, because this is the output biases. So again, it's in Rm. And it adds with the AIs, the sum of the AIs multiplied by the Tan-H values. So yeah, this is the different components. I guess I could be nice and try and add them in color to the picture over here. What color did I use? White for B. No, I've got this the wrong way around. It's white for the bias and red for the incoming weight vector. There's a picture in my thesis that does this in more detail in the preliminaries chapter. Okay, so this is the setting. I think that's all I need to mention for now about this family of neural networks. So now I'm going to try and tell you about the link between these three different perspectives on degeneracy. Okay, I'm going to start with writing up the three definitions, and then I'll show you the equivalences. So perspective one, I'll call this degeneracy perspectives. Do I need to move over? Here we go. Okay, so what are degenerate neural networks in the title of my thesis? Well, one, I think the most kind of appealing definition is not actually the one that kind of brought me to the topic, but it's the one that maybe has the most, is kind of the most evocative and suggests the most interesting kind of role of these networks in theory and practice. And so it's non-minimal networks. Non-minimality characterizes degenerate networks. So this is something like W in the parameter space with H units is degenerate if, might as well say if and only if there exists W prime in some other architecture with H prime units such that H prime is less than H. So we've got fewer hidden units, but the functions are the same. So a functionally equivalent parameter W prime exists in a smaller architecture. If you call an architecture smaller, if it is sort of defined on a networks with fewer hidden units than we started with. So this is interesting because it connects to things like Occam's razor and minimum description lengths and stuff like that. To me, anyway, I think this is interesting. These are the networks that are actually simple networks in disguise. They're using lots of parameters, but they don't need to be. Like, there's other ways maybe that neural networks could have could not be as complex as they appear to be based on the number of parameters. But this is one way, and I think it's an important way that hasn't really been acknowledged in the literature. Okay, so 2. Richer geometry. Remember, geometry is about this functional equivalence classes. So this is, I'm going to attempt to formalize that distinction that I tried to make on the first board about red sets versus green sets. So I have to remind you the state of the literature. It's been known for decades that for almost all neural networks, sorry, for almost all parameters in this type of architecture, almost all 10H networks, you can describe all functionally equivalent networks, the entire class, the entire red set, by 2 operations. One of them is permutations of the units in terms of like switching the weights between units according to any permutation, and sign flips of the units. So negating the incoming and outgoing weight vectors and the bias value of a particular unit, which because of the, if you have a look at the equation on the previous slide implementing the function, you can see that if you put a negative on the AI and also on the BI and the CI, the 10H is an odd function, so all the negatives are going to cancel out and you'll be left with the same function. So if you can do any sequence of permutations and these negations, these sign flips, then you'll end up with an equivalent parameter. And it's been known for decades that for almost all parameters, that is all. Any other transformation of the parameter will lead you to a functionally non-equivalent parameter. You'll change the implemented function if you do anything else, unless you have a degenerate network. So this is the second characterization. Degenerate, I'll put it like this. W in WH is degenerate if and only if there exists some W in, W prime in WH, same architecture this time. We haven't gone to a smaller architecture. Such that FW is equal to FW prime, but I'm going to invent some notation in place here. W is not similar to W prime, where this thing means related by some sequence of permutations and sign flips. So let me pass this and connect it to what I was saying before. There are some other parameters out there that are functionally equivalent, and the existing answers in the literature don't address them. They don't find them. Who knows where they are? Who knows how many there are? That's what I've tried to answer with chapter 4. Chapter 5, the degenerate case neural network geometry, characterizing this entire, what are the transformations, or what is the full set of equivalent parameters for degenerate networks? But anyway, this is just for our purposes another equivalent characterization. And it's also what initially got me onto this topic, because this was kind of the gap that I identified in the literature when I was sort of doing the research for my project, is I realized that this case hasn't been handled. It's been explicitly excluded in all of the prior literature. Has said, okay, we're going to find the parameters. It's almost all parameters, but there are some assumptions that we make to rule out degenerate cases, and they called them degenerate, as in kind of pejoratively. And people make the claim that maybe it's interesting future work, and not everyone is entirely dismissive of this work, but at least they, as a first step, they don't address it. They don't address this case. And they say things like, in some cases, well, who cares about those parameters? They're a measure zero subset, these degenerate parameters. And so my kind of take on that when I was reading these papers, it was, hang on a second, well, it's still interesting. What is the answer in that case? And then for other reasons, I think it's interesting to study these networks. Okay, time for the third characterization, which is the basis for all of the algorithms in my thesis. And this is the characterization in terms of reducibility, or simple conditions by which you can identify degenerate networks. Because these two conditions, sorry, if you look back at this board, these two conditions are mathematically kind of nice and simple, or maybe at least the first one is quite simple, and the second one, at least it's simple. It's the negation of something simple, but if you thought about how would you actually take a parameter and test this, how would you know if a particular parameter couldn't be implemented with a smaller number of units, or if it could be implemented with a smaller number of units without somehow searching through all of the smaller architectures and all of the parameters? And how would you know if there wasn't some transformation out there that could change that could transform your parameter without changing the function, and couldn't be described by permutations and sign flips? So these are not exactly effective characterizations in terms of effective meaning sort of useful for, if you want to build an algorithm that's going to take a parameter and tell you whether or not it's degenerate. That changes now. So the third characterization is kind of the gateway to using algorithms to work with these things, these parameters. And so this is the reducibility characterization. And it goes like this. W in WH is degenerate if and only if there's any of the following four conditions hold. On the parameter W, and I'm going to write W equals A, I, B, I, C, I, D like before. So I'm just going to refer to the components rather than like W1 through whatever that total number of components was. These are the conditions. There's four of them. Maybe some outgoing weight vector is 0. Some unit has 0 outgoing weight vector. Maybe some unit has 0 incoming weight vector. Maybe 2 units have the same incoming weight vector and bias. I'll write it like this. Bi Ci is equal to Bj Cj for some I not equal to j. And maybe they're not equal, but they are opposite. I'll write it like this. Negative Cj. So Bi is equal to negative Bj and Ci is equal to negative Cj. So if you negated one of the units, then they would fall under condition 3. Again, for some I not equal to j. So these four conditions, as you can see, are very simple. You can just look at your parameter and putting floating point precision issues aside, if you just imagine that you have actually parameters represented precisely on a computer, it should be easy to check are any of the outgoing weight vectors, which remember AI is a vector in Rn. So this 0 is also meant to be a vector, but it's still easy. Check each of the components of AI. Are they all 0? If so, degenerate. If not, go on to condition 2. Are any of the incoming weight vectors, which you can just look through the parameter and go look at one of the sort of slices of the parameter, are they all 0, etc., etc. These are very easy to check. So this condition, the kind of foundation for my thesis, the mathematical results in my thesis, is these 3 conditions, and the fact that I've called them, W is degenerate if and only if, W is degenerate green if and only if, and W is degenerate white if and only if. Well, it turns out that degenerate blue, degenerate green, and degenerate white are all equivalent characterizations, which I guess I've already told you, and I've been foreshadowing by naming them like this. But anyway, this is the key theorem that kind of is the foundation for my thesis, and it comes from Sussmann. Actually, more specifically, Sussmann shows this in the case of single output networks, 10H networks with one hidden layer. Others have shown similar results in other architectures. It turned out to be really straightforward to extend Sussmann's result to multiple outputs, so which is why I've used that as my setting. This is the proof for this. Let me see if I can discuss the proof a little bit. Some of the directions are fairly straightforward. I guess I can point to those. And then in the non-straightforward direction, I'll give I'll orally sketch out the argument, but you'll have to see my thesis and Sussmann's paper for the details. I'm not prepared to present it right now. Okay, so let's say you have a reducible network, a white degenerate network, and that is you have a network that meets one of these conditions. Then maybe you can already see how you could find how you could show that this network is non-minimal. This is worth talking about because this is the basis for the reduction algorithm, is to actually carry out these operations. But just take an example for now. Let's say that on this board defining reducibility, if you had a network with an outgoing unit weight, sorry, a hidden unit's outgoing weight vector, 0. That means the contribution of this unit to the outgoing units, the output units, is 0 to all of them. It's not connected to any of them effectively. So you can remove this unit from the network. Well, that gives you straight away a recipe for defining a parameter in an architecture with one fewer hidden units, and that is equivalent because the unit you removed wasn't doing anything anyway. It wasn't affecting the function. So removing it has no effect on the function. And therefore, this network is non-minimal. A minimal network has got to have fewer units because, and you can do similar things for the other reducibility conditions. Again, you remove the unit in the case of condition 2, but you have to tweak the outgoing bias, the output unit bias a little bit. It's straightforward. The other cases, in the case where 2 units have the same incoming weight vectors, they're basically acting proportionally to each other in terms of their contribution to the function. So you can actually merge them to have a single unit with that incoming vector and bias, and like double the output or something like that. Or well, technically you sum together the output contribution vectors. And in the fourth case, you do the same thing, but you first do a negation of one of the units, which we already discussed preserves the function. So you negate, and then you have case 3, and then you deal with it by merging the 2 units. Okay, so that is talking about white to blue. It's also straightforward, I think, to show white to green. So I'll briefly, I won't go into as much detail here, but I'll just mention it. In each of these cases, once you've removed a unit, it kind of gives you possibilities. I mean, it's actually, I think in most cases, unless the unit was like already 0 input bias and output, if you just remove the unit, you have already generated something that can't be generated. Sorry, if you just set the unit to 0 input output, let me write this down, making a mess of it, sorry. So let me talk about white to green. Just a sketch would be something like if you have a unit that's contributing AI tan H, say BI X plus C. Actually, let's pretend that this AI is already 0. If you then come along and set this to 0 and this to 0, assuming they weren't already, and if they were, just set them to something else, then what you've done, this transformation actually cannot be accomplished by negations and permutations. Or at least, you know, if you're clever with the way you choose these, maybe there's something I'm not thinking about now in my head about how there could be another unit out there that you could be effectively swapping with or something like that. But anyway, basically, it's very easy once you have this 0 here, because it gives you so many more degrees of freedom on the other parameters to generate something that couldn't be generated with negations and permutations. And that gives you, that's the definition of condition 3. Sorry, the green condition, condition 2. The other directions are a little bit less straightforward. for blue to white and for green to white, well, for blue to white, you have to somehow show that there's no other ways that you could be making smaller implementations of functions other than the ways that I've already just described by eliminating these units. That is like a fundamental property of tan H. Although it may not turn out to be unique to tan H, there are certainly some activation functions for which this wouldn't hold. And I'm not 100% clear on like the best way to characterize this property of the hyperbolic tangent function, but I'll offer you a kind of hint, which is it's something to do with linear combinations. It's like a linear independence condition. Let me see. I'll actually pull up Sussmann and see if I can get the independence condition that he gives. In my thesis, I mention this in my literature review. I discuss kind of this. I point to some other papers more recently that have given what I think looks like a much more general version of this for, actually arbitrary connection graphs, not just single hidden layer networks, but networks with kind of arbitrary graph architectures. And they've related it to there being something like no non-trivial implementation of the zero function, where a non-trivial implementation of the zero function is an implementation that can't be reduced by these kind of simple operations, but nevertheless implements zero. And I think that's got to be related to, like, you could phrase that in terms of linear independence in this case, when these functions are basically sums of tan H's. So if those tan H functions are with like different weights linearly independent, it means there's no non-trivial linear combination of them that adds up to zero. So, because that's the definition of linear independence. So these different things that I'm kind of dancing around here are related. Okay, I think I found, no, I thought I found, where's Sussmann's lemma? Found it. Okay, I'm going to write up Sussmann's lemma and just leave this to be pondered more. Okay, so this is lemma 3.1, not from my thesis, but from Sussmann, 1992, the full citation you can find in my thesis. I'm going to translate to kind of straightforward notation. Let J be a finite set of, a set, I guess it's an index set, and let so we should probably use J. Phi J in J be a family of non-constant affine functions So that's the kind of thing that you apply before the activation function. It's like a bi times x plus c. And so this is kind of a code for a BI and a CEI, or something like that. Anyway, non-constant affine functions on the appropriate input domain, no two of which are sign equivalent. I'm going to write that as the sign equivalent just means they're not equal and they're not the negative of each other. I'll just write such that there's no cases where I put it like this. Where the absolute value means what you think it means. You take the absolute value of the output of the affine transformation. Is that right? Okay. So here's the theorem. Then the functions tanh composed with these and the constant function 1 are linearly independent. So that's just what it says in Sussmann. This is something he's using during the proof of these equivalences. And actually, both of the equivalence proofs, kind of these forward directions that I'm not showing, they come down to this property. Yeah.
So I think in this lemma, as well as in your previous definition, when you say something like f of w equal to f of w prime, first of all, there's the obvious obvious requirement that they are equal on kind of a open set or non-measure zero set. Like if they are, like if the input.
That's a good point. Yeah, that's right.
And I think that's perfectly fine. But I think another one which I'm currently thinking is that, like, the domain of X can't even be bounded, right? So if X is bounded, so for example, in this lemma, I can have a affine function that, like, set the C, the displacement, to be so large that it is outside that domain. Wouldn't I? So that the input to the tanh. Yeah, I haven't completed this thought, but I'm just wondering if like X has to be like O of Rn or something like that.
Well, that's the setting that I consider, where X is all of Rn, and that's the setting that Sussmann considers.
Right. Okay.
Yeah, I haven't thought a lot about relaxing that assumption.
Okay. Cool. Okay. Thanks. Just
cool.
clarifying whether that's the.
Yeah.
Thank you.
It's worth thinking about because basically in machine learning practice, one of the ways of kind of approaching, one of the ways of making this more realistic and kind of relevant, I think, is doing the analysis with restricted domains. Like what is the functional equivalence class, for example, the geometry, when there's a domain restriction to even a finite discrete set, which corresponds to the training inputs. Because then you get to, then basically what that would be is, what are all of the functions that are equivalent according to this training set? And for example, if they also are equivalent to the training outputs, as in like they perfectly reproduce the outputs for each input, assuming that there's a unique output, a unique input for each, a unique output for each input in the training set. Then you end up with what is the set of like interpolating or memorizing solutions, and this is the zero loss set in gradient descent.
Yeah.
which may have non-equivalent functions if those functions are equivalent on the training inputs. So yeah, this is certainly a very relevant direction to work in. But as far as I'm aware, this work hasn't been started from this perspective, although there are others that work on characterizing that set. I don't think this work has been extended in that direction yet.
Yeah, that's essentially the concern I have, because usually the training set has a very, very bounded X. And I just realized what my thought was just now, which is if you take 2 units and then set one, like if X is bounded, just set C so large that the X part and the B times X part doesn't matter, and then pick another unit and set C so small that that unit is, so the previous unit is always 1, the next unit is always -1, they cancel out to be 0, and that's one way to implement a implement a linearly dependent, as in they implement a non-trivial implementation of a 0 function. But obviously they are not equal. This is kind of in the approximate equal regime.
That's right. Yeah. The asymptotes of the 10H are never going to let you get exactly 1. But yeah, that's the other thing. It's like as you have said, those are going to be so close to being equal as to be indistinguishable in practice, and this analysis is completely kind of missing that part at this point.
Yeah.
So that's definitely a limitation. Okay. So I'll just leave you with this independence property, and yeah, have a look at my related work. Sorry, the sort of last few sections of my literature review where I point to more literature on this and more results that are similar. Sort of forming a very clear understanding of this is future work for me. Okay. Any other questions? Otherwise, I think we can now move on to putting these conditions into practice and doing the minimization algorithm. All right. So I've already mostly talked about the different ingredients for the reducibility, for the reduction algorithm, the parameter reduction algorithm. It's basically this whiteboard here, the 4 conditions, and how I talked about. I'll go through it again and in more details so that you have a chance to kind of keep up, and I'm not just talking about it, but basically all we have to do is repeatedly apply this operation of removing a hidden unit with one of the reducibility conditions until the network we get is actually irreducible. I think it's the first time I've used that word. Irreducible just means not reducible, and that's the word that Sussmann uses because he's approaching this from actually the kind of opposite perspective. So he's concerned about irreducible networks and non-degenerate networks and minimal networks. Anyway, so yeah, what we're going to do now is make an algorithm that repeatedly applies these conditions. Actually, that's a really simple algorithm that you just apply these. You sort of while reducible, remove a unit and repeat, and then when irreducible, stop. You're minimal. It's worth. I'll write that up, but I won't write it in full detail because I want to do the kind of more fun algorithm version of this algorithm, which tries to do it more efficiently. But I will write this up so that it's clear why this works. Because I think to understand why the cooler version works, we've got to understand that this version works. So I said algorithm. Which algorithm is this in my thesis? Chapter 4, algorithms. Algorithm 4.9, I've called it slow reduce because the next one is going to be fast reduce. A parameter W in WH, and the aim is to output W prime in WH prime with the so that this is a minimal implementation of the same function. So it looks like this. While W is reducible, which you check by the 4 conditions, remove or set W, you sort of destructively update W to remove 1 unit. According to these conditions again. There's depending on which condition, you do it in a different way, like I kind of outlined earlier. And I can go through it in more detail if necessary, but that's basically it. When this loop ends, the while condition is false. That means W is irreducible, and so you can return the current value of W, which is going to be irreducible, which means there is no, so by the equivalence, that means there is no smaller implementation, because if you don't meet the 4 conditions, you're not reducible, and then by Sussmann's equivalence, you're not non-minimal, which means you're minimal. So that's it. That's the algorithm. I just wanted to make sure that everyone's clear on that this worked, and that it uses the equivalence kind of in order to I guess I can write down what this algorithm actually does. Theorem. The W prime is functionally equivalent to W, and W prime is minimal, which means there's no smaller parameter that implements the same function. Yeah, any questions about this? Okay, let's turn to fast reduce then. Oh, I should double check the chat as well. Okay, all good. Fast reduce, algorithm 4.12 in my thesis. It does the same thing in terms of sort of its input-output behavior. It takes a parameter with h hidden units and produces an equivalent parameter with actually the same number of hidden units. Same number as the slow reduce algorithm will, because it's minimizing and there's only 1 unique minimal number of units required. How it does so is different. I guess I should point out what's wrong with slow reduce. Why is that slow? Depending on exactly how you implement this high-level sketch of an algorithm, you might be looking at checking each of the conditions in each iteration in that first line during checking whether or not W is reducible. And that's some kind of like quadratic operation, because you've got to check all the pairs to see if they're proportional, if they're equal or negated, and that's going to be quadratic in the number of hidden units. And then removing a unit, I guess, is going to take like linear time, because you've got to modify the unit to potentially remove 1 or whatever. I mean, you can think of more clever ways to do this, but fundamentally, kind of naively searching for conditions to apply, it's not clear that that will be fast. You might spend a lot of time checking for conditions. So what we're basically trying to do is come up with a clever order in which to apply those conditions, so that we'll only have to go through the list of conditions like once, for example, or a couple of times. And this is the algorithm to do that. I'm going to sort of sketch out how it works in terms of, it's going to work in 3 phases. And I'll talk about why that works. Actually, I think I call them stages. No, passes. Pass 1, because we make 3 passes through the parameter looking for things. So in pass 1, we identify plus remove the units with 0 incoming weight, because they're not going to be in the final parameter. So I'm going to fill in the code for that in a moment. In pass 2, which is a little bit more complicated, we identify and merge units that have shared incoming weights and biases. Or I guess I'm going to put an absolute value here to represent that we're looking for either these vectors are equal or they're negated. In my thesis, I defined some notation for the absolute value of a vector, which is like the positive or negative version of it, but it is a vector rather than a scalar or something. It's not the same as the magnitude of the vector. Okay, so fill that in. And then pass 3 is to, okay, so this has taken care of condition 2. This takes care of conditions 3 and 4. And so it remains to take care of condition 1. I've left it 1 until last because when you're merging units, it might turn out that the merged unit suddenly has outgoing weight 0. And so if we got rid of all of the units with outgoing weight 0 in the first pass, we would then have to go again and look for units with outgoing weight 0 in a fourth pass. So I just decided to put this pass last, and then we'll get all of the units that originally had outgoing weight 0, we'll get them now, or we will have merged them into units and we don't need to worry about them because they're not going to count, or any new units that have been merged and now have outgoing weight 0, we'll get those in this pass as well. So let me write down what I said. Identify and remove units with outgoing weight with AI equals 0. And this is AI after merging. So let's do this in code. I guess it's as simple as just defining a set of units that we're going to continue with, which I'm going to call I. And I'll let that be the set of units such that BI is not equal to 0. And so this abstract pseudocode, it's enough to just define this set. But if you're thinking about an implementation, this is like a linear operation where you just scan through the list, check if each vector is 0. And if it's 0, you discard it from the list that you're considering. And if not, you keep it. It's important at this point to define, I didn't kind of mention earlier, but in detail, but when you go to remove a unit like this, it means that somewhere in your sum, you have something like AI tan H 0x plus CI. This is not actually 0 unless CI is 0. So this is nothing, but AI tan H CI is a constant. You can still remove this unit because you can just fold this constant into the output constant. The output units have a bias, and you can just fold this into that. So I'm going to define the final output bias for the new parameter here as the original bias, which remember with our notation is D, plus the sum of all of the removed units left over bit. So any I that is not in this set that we're keeping with non-zero. So these are all of the I's for which BI is 0. And then I'm just going to add up AI tan H CI of those. Okay. Any questions about pass 1? Otherwise, I'll move on to pass 2. Okay, pass 2. This one's a little bit trickier, but grouping these units, to avoid it being quadratic, what we can do is we can sort the units by their incoming weight and bias vector. If you think about sorting vectors, I don't know how many people here came to the meta-uni algebraic geometry course, but you may otherwise also be familiar with something like the lexicographic order of tuples. In MAG, we used it for ordering tuples of powers of sort of monomials, or ordering monomials. But here we could use it to order vectors. We can just It doesn't matter what order we use, though. I just need a way to run a sorting algorithm, which is going to be n log n, or h log h or something, but h is the number of units. Because then after I've done a sort, it's easy to identify identical pairs because they're going to be next to each other in the list. So I don't need to do some kind of quadratic operation to find all of the groups that are going to be merged. So the way that I'm going to represent that in pseudocode hides a bit of that detail, but I'm just going to write, I'm going to define pi 1 through to pi k. This is the number of groups there are going to be, where this is a partition of I by the relation I is grouped with j, if and only if this kind of lexicographic absolute value of bi ci is equal to the lexicographic absolute value of bj cj. In other words, if these two parameters would meet conditions 3 or 4, group them together. And to implement this partition, you first negate all of the units until they're kind of lexicographically positive, so that condition 4 will never be active. It will always be condition 3. And then you sort them in n log n time, where I guess n is actually h. And then you just go through the list and you read off the groups one after another. So this can be done in the time it takes you to sort the units. After doing that, we have to compute the new value for each of the units. And these are going to be some of the units in our final network. So I'm going to use some more Greek letters like the delta here. So for each of these groups, for I equals 1 to k, I guess, I'm going to create a new unit, which I'm going to call alpha I is going to be the outgoing weight. That's going to be all of the outgoing weights from the units in the group, pi I. But I have to make sure that I get the sign right. If we flip to the sign, then I'm going to want to flip the sign of the outgoing weight as well. I'm just going to simplify it here and write plus or minus. And in my thesis, I've got some more complex notation that allows me to keep track of exactly which sign to use. So this is plus or minus a j, where j is an element of the group number I, the partition cell number I. And then equally, I'm going to define beta I and gamma I, the equivalents of b and c, to be just the plus or minus b, bj, cj. Actually, it doesn't matter which j you use. For some j in the cell, it doesn't matter which j you use because they all have the same plus or minus if you use the right plus or minus. Like you can just pick any because they're all equal. That's what we sorted on. Oh, sorry, that's what we grouped by. So these units now from I equals 1 through k with the weights given by alpha, beta, and gamma are going to be our unique merged units. Unique in the sense of conditions 3 and 4 over here. There's going to be no overlap in their incoming weight and bias vectors, and there's also going to be no negative overlap. But we have one more pass because this step here could create some alpha i's could be 0. Or maybe, even if it's in a group by itself, it wasn't by merging. Just the original AI or AJ or whatever was 0, and then this might be 0. So let's do a final pass where we just define those. I guess I can call it R equals the ones that we want to keep, not equals. Oh, I switched to using equals. How evil. instead of the gets. I apologize for that. I'll fix it here, but I won't fix it in pass 2. Anyway, R is going to be those I in 1 through K. Initially, this I up here, this was actually 1 through H. I guess that was implicit. But this one is through K because we're counting through the merged units, and there's only K of those, such that alpha I is, let me say, not equal to 0. And so R is actually the indices of the units that we're going to keep. I'm getting a little, this is a little tricky with the indices anyway. I think it, like the idea is clear here, but you got to decide which subscripts you want to use. So then I'm going to write the final value that we return is, importantly, it's the units that have the indices R, and then it's delta at the end. But I guess I have to write it in some weird way, like alpha I1 through alpha IR, because it's not just 1 through R or something, because it's some subset R where, anyway, R is equal to, this should fix it, R is equal to I1 through IR. Anyway, then there's the betas. And the gammas, I'm just going to write I1 through IR. And I've just run out of space, but there's only one more component, which is the delta output vector, output bias vector. And that's it. Now, this parameter is a neural network parameter for the architecture WR. Sorry, my mouse just lost sensitivity for a second. My trackpad. This parameter is in WR. R is this minimal number of units, which is what I call the rank elsewhere in my thesis. And that's why I've used R in this algorithm. And this parameter of R units is going to be equivalent to the original. Maybe that's a little bit trickier to see with this algorithm, but I show in my thesis how each step of this algorithm carefully keeps the equivalence with the original parameter, because we only eliminated according to operations that preserve equivalence, and we only merged units in ways that preserve equivalence, if we're careful with these signs that I've been a little bit lazy with today. So that's the fast reduce algorithm. Any questions?
It's fast, but is it fastest?
The fastest? Well, it's a little bit tricky to have this conversation because, well, let me tell you, this is like sorting fast. This is as long as it takes to partition these things. Everything else is linear. That sorting step is probably going to take n log n, but it depends on the representation you're using. Are you using floating point numbers, for example? Then you can do operations with floating point numbers in constant time. If you're using some other complex representation of your numbers, maybe things are going to be a bit slower. If you care about these kind of computational issues, though, you're kind of missing the point of
I don't care about that.
This, which is like an ideal. This is an idealized algorithm to some extent, and like because of all those conversations we had earlier about exact equality versus approximate equality being in practice just as important. This doesn't count for any of that. But yeah, I think it's fast in terms of the number of operations. I haven't thought about whether it's fastest. I guess under certain circumstances with the numbers that you're dealing with, like if you have certain assumptions on the units, or if you have some certain way to partition them more quickly, which sort of is a representational condition, like it depends on your representation, you can probably do better. But I mean, sorting can happen no faster than n log n for comparison-based sorting algorithms. And non-comparison-based sorting algorithms can sometimes go faster, but it depends, again, on the representation. So yeah, I would say it's probably the fastest under reasonable assumptions.
I have a question.
Yeah.
This is not the canonicalization algorithm you mentioned before, right? This is
That's right.
Like one step before that, right?
Yeah, it's half of the canonicalization algorithm.
Right. So it's like I'm guessing the canonicalization would be sort of making unique choices at each stage regarding the sign or something like that.
Yeah, well, actually, this makes consistent choices with the sign because it makes everything positive in a certain way of defining positive. So, and actually, if you sort these partition cells in lexicographic order, then this actually is a canonicalization algorithm.
Right.
It will always produce the same partition cells for the same, no matter the order of the original vectors, because if it does it based on lexicographic order. So this is pretty much a canonicalization algorithm. In chapter 5, I go and show that if you compose this, if you do this operation, which gives you a minimal implementation, and then you apply an algorithm that specifically sorts the units by their lexicographic absolute value of the incoming weight and bias vectors, and you also standardize those. Well, yeah, I said absolute value, so that covers it. So if you take care of the, in other words, if you take care of the negation and permutation symmetries, then you get a canonicalization algorithm. I guess I could have written this a little bit more carefully to make it a canonicalization algorithm, but it wasn't the point of that at this point in the thesis. But yeah, it actually almost is.
Right. I guess my question is, so this is kind of a proof that every function implemented by the network has a canonical parameterization that implements it. And my question is whether or not the move that changed the canonical to non-canonical moves like something like sign flips and some sort of merging, which looks like they're always sort of not in the neighborhood of the canonical parameter.
Yeah.
Is that correct? So
sorry, I missed the question. Yeah, say again.
So in a sentence, the question is whether or not there are other equivalent parameter in the neighborhood of the canonical parameter.
Yes. Unless you didn't remove any units. If it was already minimal, then by Sussmann's, if you put the right angle on Sussmann's result, it shows that you've only got these permutation and sign flips. And like you said, they all take you an epsilon away. Actually, it's not immediate to show that, because like you could have a 0 unit a priori. You could have a 0 unit, and then if you apply a permutation, so a sign flip to that unit, it's not going to change it. Well, that would not take you in the neighborhood. It would, like, you'd be at the same parameter still. But anyway, that is going to turn out to be non-minimal. So, but anyway, it's a theorem that for a minimal network, there is a neighborhood around it in which it is the only equivalent parameter. In other words, you could say that the implementation map, the map that takes parameters to functions, is locally, well, this is actually stronger, but it is true, locally injective around irreducible parameters. Anyway, but the converse case, the case of the non-minimal parameters, then definitely these functional equivalence classes are actually connected, and they're continuous. And how can you see that based on what we've done? Imagine, go back to this second slide on second board on the second group here, and have a look at this this quick example that I gave. make sure I move out of the way. This quick example that I gave here, basically, this is for the case of AI being 0. If AI is 0, then you can imagine perturbing BI and CI any small amount, and you will not change the function because this unit is completely not contributing to the function. So they can be anything, and therefore, they can also be arbitrarily close to their initial values. Does that make sense?
Yep.
Yeah, and so this is just one of the conditions, but for the other conditions, there are similar cases of kind of local variation that you can do, and you can always do at least a little bit. So if we look at those conditions again, back on the first slide of this group, that was I. For II, it's a little bit less straightforward because of that constant thing that I talked about. But basically, if you modify AI and CI in just the right amount, you can keep AI times tan HCI constant. Like think if you increase CI a little bit, that will, tan H is monotonic, so that will increase tan H. But then if you decrease AI a little bit to account for that, it's actually like a non-polynomial relationship there. It's an analytic relationship, but you can do it, and so you end up with a neighborhood, not an open neighborhood, but a neighborhood where you can vary them. And the other case is sort of similar. I can go through that if you want.
Yeah, so the idea is that in the reducibility condition, once we, if we don't have 1 and 2, like if we don't have the situation in which we're in 1 and 2, then we any equivalent parameter is epsilon away.
Sorry, I didn't quite understand that. If you don't have 1 and 2, as in conditions I and II, or
I and II, that's correct.
Yeah. So in this is the merging cases. I'm not quite sure what you mean by any equivalent parameter is epsilon away.
Any equivalent parameter that doesn't involve zeroing out new nodes or something like that.
There are parameters nearby that do not involve that, but not all of the parameters. Okay. Some of them will be further away as well.
Okay.
Let me show you the ones that are nearby, though. Let me see. So if you have these equal, then you've basically got, I'll add a new color here. You've basically got a situation like AI tan H BI X plus CI plus AJ tan H. And I was going to write BJ here, but because BJ is equal to BI, I'm going to instead write BIX plus CI here. And you can see now that these two bits are equal. So what we've really got is, what really matters is the sum of AI and AJ, which means you can add epsilon to AI and take it away from AJ, and you won't change the function. Does that make sense?
Yep.
But to kind of clarify the other part of your question, as phrased at least, if you added negative AJ to AI and also to AJ, now you have a unit that has a 0 parameter. So you can also go further away. So it's because you asked if all of the equivalent parameters were within epsilon. That's not true, but there are parameters within any epsilon. There are equivalent parameters.
Yep.
Cool. Great questions. Any other questions?
How much harder does it get if you add another layer?
Okay, great question, and a very, I think, important one. And I think not as hard as you might think, but it does get significantly trickier. So let me see. The state of the art on this is, so we have non-degenerate geometry for multi-layer networks basically figured out. I'm not sure if there's a very clear, Sussmann's 3 equivalent conditions result in these multi-layer architectures. I think there probably is. I have to pass that literature a little bit more to say for sure. But certainly there are, there's like Fong and Lampert 2019 is a well-known paper that took ReLU multi-layer networks and gave some conditions, not necessarily optimal conditions, but conditions under which the only symmetries are like some simple set of symmetries. So that's the non-degenerate case. Then if you want to study the degenerate case, you want to ask, well, what are the optimal conditions? And that in this case, corresponding to the reducibility conditions. And these are the ones where it's not just that if you satisfy these conditions, you want something like if you satisfy these conditions, then there's a minimal network. Now, in one direction, the rest is really easy because if you have that condition, you can just apply these local operations where you just remove a unit one at a time. You can do that on each layer kind of independently. I mean, obviously the layers are connected. If you remove one unit, you have to do some operations affecting its connection to the next layer. But you can do those, and you could just do them one layer at a time. You just like handle the second to last layer, like the last hidden layer, and then make that minimal, compress that as far as it can go, and then go to the next layer in the network and so on. I think these algorithms are going to be really simple. It's then the proofs that are related to them that get a little bit more complicated because, for example, as soon as you have two hidden layers, you can no longer be naive about the domain, and the issues that Edmund was raising earlier become important. So, for example, what if the first hidden layer does a transformation of the inputs so that the inputs are all positive or something like that? Well, now your network, for your second layer, it's not enough for the second layers to be equal on all inputs. They have to be equal on only positive inputs because that's what they're getting from the first hidden layer. But when we had only one hidden layer, we could make that naive assumption that we care about all possible inputs. But when you have a layer beforehand sitting right there that could be meaningfully restricting the kind of inputs that you're getting, you can no longer take that for granted. And I think it becomes vitally important to take account of that case. But yeah, if you probably had like some open, basically I think if you don't collapse if the first layer doesn't collapse the function outputs to like 0 or something like that, it's not gonna matter too much because you'll still have some open subset or something like that, and then your activation function is probably analytic or at least piecewise analytic like ReLU, and you can probably deal with it. So yeah, I think it'll be more tricky to do the geometry part and get Sussmann's theorem. Once you have Sussmann's theorem, once you have some simple reducibility conditions, you can probably just deal with that layer by layer. Even the geometry, you can sort of decompose by the layers. But like I said, then you have to be a little bit more careful in terms of domains and stuff. Yeah, that's my answer. Great question.
Cool. Thanks.
Oh, I should also say that paper that talks about the non-trivial implementations of the zero network, they do start to, that's the starting point that I would use for this in future work. I kind of found that paper late in my project and scrambled to understand it and kind of place it in the context of my work. And basically my understanding is they consider actually, they don't give like an explicit algorithm, but they say that, in principle, you can apply these reduction operations multiple times, and then you end up with an irreducible version of the network you started with that just takes advantage of these simple operations. It's still open, like what that would look like as an efficient algorithm for applying those operations. In arbitrary, this is the one that deals with like arbitrary connection graphs. So it's a very general setting, including multiple hidden layers, easy. Yeah, that would be the starting point for future work on this.
So what's the plan for the second part of this, whenever that happens? If there is a second part? Another SLT day, I could go through, we basically,
it's probably, if there's demand, I can go through chapter 5, which is the degenerate neural network geometry, talk about the functional equivalence class a little bit more. But it's not too much more interesting than this. The connectivity result is a little bit interesting, I guess, and kind of nice to present. I've already actually sketched that out in a previous SLT session, so maybe not urgent. I have also sketched out chapter 6, which is the NP completeness bit, in a previous one, but I could go through that in more detail, and having written it all up now, I think I could do a better job of it. I would say that's probably the next step, is to say, well, okay, you've seen rank now. We basically got to rank. So just to finish the presentation then, having a reduction algorithm, it's now trivial to compute the rank of a neural network, because you just reduce it and then count the units that you're left with, and that's the rank. But in chapter 6, I go on to show that if you want to define some kind of approximation or relaxed version of the rank, it's not an approximation of the rank, but it's like a rank based on approximate degeneracy rather than exact degeneracy. Then there's not necessarily going to be a fast algorithm. Unless P equals NP, there won't be a polynomial time algorithm, because, as I show, that computation is dealing with NP completeness. And that I show by reduction from a problem called SAT, as in Boolean satisfiability, which I sort of place some restrictions on to kind of make it a little bit simpler and show that it's still NP complete. And then I convert that to another problem that I call uniform point partition, which is about clustering points in a plane using small rectangles to kind of group points that are nearby together. And those small rectangles actually they're squares, not just rectangles. Those small squares correspond to like which units have nearby weight and bias vectors that you would like to merge together. But it turns out that choosing exactly which ones to group that are nearby, if you want to merge them, you can set up a problem, you can set up a parameter where making those choices is equivalent to like solving a SAT problem, because the choices kind of correspond to true or false. And then you can make the choices have consequences that ripple throughout the plane and end up like linking together in the structure of the formula as clauses and variables. And so I could go through that proof in some detail, because I think it's like a fun, these reductions are always quite a fun part, I think, of computational complexity theory. Maybe some people here have done that kind of thing before, and maybe you agree, maybe you disagree, that's fine too. But yeah, I quite liked this part of my thesis. It was kind of more to my background strengths in theoretical computer science. And
yeah, I think that would be worth, in principle, I guess you've covered at a high level some parts of it. Yeah. But first of all, it's always worth covering things multiple times. Secondly, the thesis is now available for people to do their homework beforehand. And thirdly, at least one person here, so Ben, is looking at renormalization of one hidden layer 10H networks. And this probably has some significant connection to this problem. So he's in particular interested in understanding this deeply. So giving him and other members of the audience who are interested to maybe build on this a chance to read the document closely and then come to your talk, I think we could profitably revisit this. Yeah.
Fantastic. Yeah, well, I will mention that, yeah, I put the draft in the Discord channel. And once again, it's a draft still, but I hope in a couple of weeks to have not only received the mark from the examiners, which I'm sort of dreading a little bit, but also to have a final version that I'm going to be happy to share more widely. But yeah, like I said, there won't be many changes other than fixing typos. If anyone does happen to see any typos, please let me know, because I'm going to be looking for those as best I can, but I'm sure I'll miss some.